Today's lesson, 9.2, Similarity Transformations, really takes the review work that we did in 9.0 and the work that we did in 9.1 and blends it all together. So if you haven't given yourself a good understanding of the past lessons that we've done, then please go back and review those first, because this will be jumping right in here. In the very beginning here are some of the reminders of things that we have been talking about. So I'm going to go over these really briefly. I would encourage you to pause the video or maybe review your notes and take a little bit more time here before proceeding on to the new material. So just to get started, what are congruent figures? Congruent figures are figures that have the same exact shape and size. So corresponding sides are congruent, they have the same length, and corresponding angles are congruent, they have the same degree measurement. They're the exact same, they just might be oriented a different way. Similar figures are the same shape but different sizes. So think about something being extended out or shrunk down by a common scale factor. So for here, corresponding angles are congruent, the corresponding sides are proportional. All right. The three types of transformations that we reviewed from Math 1 were translations, rotations, and reflections. These are all rigid motion transformations, which means the shape of the shape and size of the figure doesn't change. So a translation is when I just slide something over. So usually I have a capital T, and then I've got whatever I'm doing to X and whatever I'm doing to Y in these little triangular brackets on the bottom here. A rotation is going to be when I spin a figure about a point. Now for this class, for this year, we are only doing rotations about the center of rotation at the origin. Okay. Thing to note here is that a positive rotation, a positive degree is always a counterclockwise rotation as a rule. So they don't have to specify whether it's clockwise or counterclockwise. We need to know that if it's positive, that means a counterclockwise rotation. And when I'm talking rotations, I'm using these little lowercase r's. And for our purposes, we're just doing anything that's a multiplication of 90 degrees. A reflection is a mirror image or a flip over some line. The two lines that we'll be using in this class are the x-axis and the y-axis, but it could be any line. Now I've got the rules here written in blue for how do the coordinates change for rotations and reflections, and you can use those as tools going through this section. Not necessarily something you need to memorize, but something you need to know how to use. And then the bottom one here, dilations, this is what 9.1 was about, and this was a new transformation. And this is when I take a figure and I multiply the lengths of the sides and or the coordinates by a common number called a scale factor. And then that creates something larger or smaller, but it's the same exact shape. A dilation creates a similar figure, not a congruent figure. So the example here is that if I have a dilation of 0.5, that's a dilation of a half at the origin. So as long as I'm doing it at the origin, that means that to get my new x coordinate, I would take half. To get my new y coordinate, I would take half. Right? So again, a good note here, creates a similar figure. The other ones create congruent figures. All right, so that's a brief overview of what we need going into this section. Okay, now on to the new material. Composition of transformations is when you're going to perform a transformation of a transformation. And that could keep going. I could perform a transformation and then another transformation and another and another. I could do it infinite number of times. It's this new idea of taking a function of a function, a transformation of a transformation. It actually is, it's a whole new entire operation. So you're going to see this note here where I wrote composition with an arrow pointing down. This little circle means composition. It's in the middle of the text here. If I have a little circle that's kind of above a superscript, if you will, that's a degree symbol, right? So, ooh, that's not gonna, can't see that. So 90 degrees is a degree symbol, but if I'm talking about R composed with T, this is composition. All right, so one is above and one's in the middle. It is a little circle. It's not a dot, which means multiplication. Entirely different thing. Now, the part that is important to remember here is we actually work our way right to left instead of left to right, which is a bit counterintuitive. And you can think of it this way. You can think of like when you're doing your order of operations, you know how when we're simplifying something, we have to start on the inside and work our way out? That's the idea here. So let me walk you through this picture here. My original triangle is this blue colored one, PQR. And I'm going to create two transformations. So my first transformation is a slide to the right. Okay, so that slide to the right is 10 units. Let's see. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and I get to my new R, or my R prime. And I can do the same thing for P, and I can do the same thing for Q, right? I go to the right 10. That comes from this right here. This is the first step. So I translate right 10. And then I work my way out from there. So I do that first, and then when you look at this picture here, now I've got this pink triangle. So how do I get the pink one onto the green one? So now I do a reflection. Capital R is for reflection. So I'm going to do the outside one second. And then I reflect across the x-axis. Right, here's my x-axis. So when I'm reflecting, reflections preserve distance. So you'll notice like from Q prime to the x-axis, that's 1 unit. When I reflect it, that means from the x-axis to the new point is going to be 1 unit. Similarly, if we look at P, right? What is the distance from P to the x-axis? Because that's where we are reflecting about. So 1, 2, 3, all right? And then I can count 1, 2, 3, and I can get back to P double prime. Okay. So then this green one is my final answer. So the point of this, and we're going to drive this home with the little two kind of explanations underneath here, is I'm starting on whatever's closest to the inside and working my way out. So for the next one down here, what am I doing to ABC? So what is my plan of attack here? Well, I have to do what's closest to it first. So the first thing I would do to triangle ABC, and this is just like it's like a mini example, right? We're just kind of honing in on that, on what all this notation means. So I'm going to reflect across the y-axis first. And then I would work my way out. Then I would rotate, so little r stands for rotate, 90 degrees. The O there stands for about the origin. Now, when I first put out these notes, I didn't finish editing this, so it doesn't make any sense. You can just cross that middle one out, and we'll just jump to the third one. The last one over here. Okay, so I start on the inside. What do I do to GHI first when I start this transformation? So first I'm going to translate, which means slide. So remember, the first one is X, the second one is Y. So if I have a -1 in the X direction, that's going to be left 1, and a +7 in the Y direction is going to be up 7. And then I work my way out. D with a subscript of 1/2 means I'm going to dilate by 1/2. So I'll multiply all of the coordinates by 1/2. I'm going to go back through and read how I would read all of this terminology to you. So this one that we just said says a dilation of 1/2 composed with a translation of -1,7 of GHI. Let's go back over to the left one, the first one that we wrote over here. Okay. This, if I were to read this out loud, would say a rotation of 90 degrees about the origin, composed with a reflection across the y-axis of triangle ABC. All right, so that's kind of the abstract. Let's go ahead and get after it and do an example together. A similarity transformation is going to be a composition of one or more rigid motions and a dilation. So think of this as, how do I create a similar figure? I can do a translation or reflection or rotation, but I also have to do a dilation to make it similar instead of congruent. So rigid motion would be a reflection, rotation, or translation. Rigid motion means it doesn't change the size. Like if you physically have a tile that is that size, you can't just like change it in real life. Easily anyways. Example 1, graph the image of our rotation of 90 degrees about the origin, composed with translation of 2, -4 of triangle ABC. Something I wanted to bring your attention to that I missed up here is you'll see that now that we're doing multiple translations, we go from Q to Q prime to Q double prime, right? So reminder that those are just little apostrophes. They're not ones in the exponents. It's just a little apostrophe. And you can continue to make more prime numbers or prime letters. Try not to put too much stock in which one has 1 prime and which one has 2 primes. It's not really very prescribed and very precise. Kind of try to go with the flow and be a little flexible here, because some things are going to be, they're just not going to be perfect. All right, example 1. So the first thing that I'm going to do, I'm going to have these points A, B, and C, is I'm going to translate them. And you can do this visually, or you could do it algebraically. I'm going to kind of show you both. So if I do this visually, follow my cursor down here, okay, to A. If I translate this, this is 2 to the right and down 4, right? So right, 2, down 4. So I go right 2, down 1, 2, 3, 4. Okay. And I get this new point here, which we can call A prime. Visually is easy, you just count the squares. Another way to do this would be to take the coordinate, right, and take whatever x is and add 2 and take whatever y is and add 4. So you could do this algebraically also. So if I look at this coordinate for a, 2 comma 4, if I add 2 plus 2, I'll do this one really slow. And then if I do 4 minus 4, right, then I get a prime is 4 comma 0, which is the same thing if I move it visually. So if I take B and I go right 2, down 1, 2, 3, 4, and I count, I end up right here. Or if I focus more on my coordinate here, -2, so I would add 2, and then I have 8, and I would subtract 4. So this gives me 0, 4. So different ways you can do it. You just do whatever works for you. I like to just kind of do it visually. It works for me as long as I've got a good picture. Okay. So I have a new triangle. It's translated down. Didn't change shape. Actually oriented the same way, just slid over. That's the first step. Now I'm going to rotate it. And if you look back above, or if you remember, when I rotate something 90 degrees, I'm going to exchange the x and the y, and I'm going to take the opposite of the first coordinate. So I prefer to not do these ones visually. I like to look at my coordinate to do this. Visually, I would need to draw a line from A prime to the origin and then draw something with a 90-degree angle, which is totally doable on paper, a little bit harder. I mean, it's not that hard. I guess you could make a square, but again, it's a little bit funkier digitally. So here, I'm just going to exchange 0 and 4 and make the 0 negative. Oh, wait, 0 can't be negative. So 0, 4 is all I got. That's actually right on top of B prime. So this is now A double prime. All right. Then B double prime. So I switch the 0 and the 4, and I change the sign of the first coordinate. So -4, 0. And then C double prime, I exchange the 6 and the 2, and I change the sign of the first one. So -6, which doesn't exactly fit. It's almost there. Up 2. There we go. If you like, since this is my final answer, you might want to like shade it in, make it stand out. If you're using different colors like I am, then it's pretty easy to see. If you're doing it all in pencil, you might want to just do something to maybe make it bold, shade it in, use a different color, highlighter, something like that to make your final answer stand out. I had a student ask me like, oh, it's too much, I can't see what's going on. Is it okay if I do it on different graphs? That's fine too. Okay, Now on example 2, we have PQR again, and this time the coordinates aren't written out for us, so I'm going to go through and just identify the coordinates. And that's on purpose. That's just to give us a little practice, like this is 3 over and then up 5. Remember that every coordinate is always x, y. X is left and right, and y is up and down. So we always go left and right first. So to get to to get to R from the origin, I go left 6, then up 4. All right, so the first step here is I'm going to do a rotation of 90 degrees. And when I rotate, perhaps you remember, I exchange my x and my y, and I make the first part take the opposite. So if it's negative, I make it positive, and if it's positive, I make it negative. I take the opposite. But this little, these little directions here is what I do to it. It's not what it needs to look like. It's what I do to it. Okay, so P prime. Instead of 3, 4, I'm going to exchange the 4 and the 3, and I take the opposite sign of whatever's first. So I have negative 4, negative 3. Oh, negative 4, positive 3. Almost goofed that one up. So here is P prime. All right, then for Q, exchange 2 and 0. Make the first one the opposite, but 0 doesn't have an opposite, so that's just going to be 0, 2. And then for R prime, I exchange the 4 and the negative 6, and I make the first part the opposite. It's positive, so it's going to be negative 4. So double check. It doesn't have to look like negative y comma x. It's just what I do to it. So I switch it, then I take the opposite of the first coordinate. So negative 4, negative 6. And I just realized I have an error. This isn't quite right. The point's 3, 4. I mean 3, 5, not 3, 4. So, sorry. I wrote it correct on the paper and then copied it down wrong. So I have to make a couple fixes here. So this is going to be negative 5, 3. Sorry, so my error was that I copied the coordinate wrong from my picture. There we go. Now it looks right. So my first transformation done. Second transformation is going to be a dilation of 2. So what I'm going to do is I'm going to take 2 times every x value and 2 times every y value because I'm dilating from the origin, which makes things easier. If this video is going too fast, please slow it down. I don't want to glaze over anything super important. So I've got negative 5 comma 3. I'm going to take negative 5 multiplied by 2, 3 multiplied by 2, and I get the point negative 10, negative 6. Nope, negative 10, positive 6. Oop, and I only went up to 5 on my graph, so I'm just going to estimate where that would lie. Zero, 2. Multiply this by 2. 0 times 2 is just 0. 2 times 2 gives me 4. And when I multiply the coordinate -4, -6 by 2, I get -8, -12. So -8, and then down shoots down 12. If you're doing this on paper, you should absolutely be using a straight edge, whether it's a ruler or a side of a book or a side of a card or a phone or whatever you've got. Definitely be using something to make your lines nice and beautiful and straight and perfect. If you're doing it digitally, I know it's a bit harder, but hang in there. Now, another way I might want to make this answer stand out is I might just make it like bolder. I might just make it more thick. Like that. Example 3. Explain what possible transformations can map DEF to triangle B prime, E prime, F prime. So on this last one, well, not this last one, but this third problem, this is a little different. So I want you to take a moment and try to visualize in your head how you could take the blue triangle and use some transformations to get it to the red triangle. Now there's multiple correct answers for this. You can do it in 2, or you could do it in like infinite. You could do it in a ton. But okay. So we may have all come up with different things. I think the easiest way to see the transformation, which could totally be different from how you saw it, I think the easiest way to see this transformation is to see a reflection first and then a translation. So I'm going to go ahead and I'm going to walk through what that would look like. I know it's got to be a reflection because everything is like a mirror image, right? In my original picture, D and F are closest to the y-axis, and then when I move over here, D and F are still closest to the y-axis. Okay. So when I reflect this across the y-axis, D is 3 units from the y-axis. So if I go 3 more units in the other direction, I get a new D. And same thing for F. It's 3 units away from the y-axis. So when I reflect it, I get a new F. And then E is 5 units away. So I reflect it over and I get a new E. So I end up with this triangle. So from there, I can slide it over. So if I reflect first, and then I slide. So how do I get D to D? So this is what I was talking about, like try not to put too much stock in the 1' or 2'. You know, it's not perfect. So I could even call this like double prime up here and then move it to single prime. I don't know. Not quite content with all that all works. So to get from my purple D to my pink D, or my purple D to my red D, I'm going to go left 2, and then I'm going to slide down 1, 2, 3, 4, 5. And if you check F and E, you go left 2, down 5, left 2, down 5, I'll end up all on those points. So again, that's not the only way to do it. There's other ways to do it, but this is, I think, the easiest and most obvious way to see. So a reflection over the y-axis for triangle DEF, and that's composed with what I did second, which was a translation. Left is -2, down is -5. So I would get this answer. Get that down because I'm going to erase my drawings that I did on the picture, and I'm going to show you another way. So let's say I scratch all of that, and that's not how you saw it. You're like, I don't really get that way. That's fine. Let's look at a different way. Let's say instead you reflected, you moved it first and then reflected. Okay. So I could also take D and I can move it to the right 2. And F. So if I move everything right 2, okay, and then I take it down also. So right 2 and then down 1, 2, 3, 4, 5. I would get to this point, and then I could reflect it over the y-axis. So if I move F down over 2, down 1, 2, 3, 4, 5, here would be F. And if I move E over 2, down 5, here would be E. So I could translate it first. Oh, rough looking. And then I can reflect it. Right, and then I can hop it over. So this, in this case, I would translate right 2, down 5. And then I would reflect. So notice that when I rewrite this, when I do the translation first, now I have a +2 to the right and then down 5. And then a reflection over the y-axis. Compare those. They're not the same. The transformations are different depending on the order. And it's crucial that they're done that way. Okay. You could also come up with a whole bunch of other things, right? You could rotate it one way and rotate it another way and slide it back and flip it and dilate it and make it smaller, which is all unnecessary, but you could do 10 things and still get to triangle D prime, E prime, F prime. Okay. Example 4 and 5, I created without a very specific grid in an effort to give us all practice with making our own coordinate plane and making sure we're labeling and giving us kind of that skill as well. So example 4, given triangle STU with these vertices, what are the coordinates of S double prime T double prime U double prime after the transformation of rotating 180 degrees composed with a reflection across the y-axis? The first thing we need to do is we need to draw in our coordinate plane. Now, I'm going to warn you, this is not going to be pretty and it's going to bother me, but it is what it is. So I'm going to draw on a y-axis. It's going to drive me crazy that it's not straight. And there's nothing I can do about it. And I'm going to draw in an x-axis, which will inevitably turn out a little bit better. I have to label these axes. So it is imperative that you label a scale on the x-axis and the y-axis. I'm going to zoom in a little bit here to make this a little easier on our eyes. I know that this grid is kind of light and small. So let's see, 1, 2, 3, 4. I'm still counting by ones, but I'm only putting a number on every other box, and that's just because these boxes are really small, and it could get very cramped if I numbered every single box. So just personal preference. Maybe if you have bigger grids, you do label every box. Maybe you don't like labeling every box, and you just label maybe out to 5. When we're in person, if a student were to turn in a graph to me that did not have the axes with a scale, I would hand it back to them. So it is crucial that you've got, or that we have all of these numbers on here. Okay. So when I plot points, remember that every point is always x then y. So I go left and right first. So to plot S, I go -5, which is left 5, and then up 6. T is the point 1, -2. And U is -3, -4. I'm going to reflect over the y-axis first. So you can do this visually on the grid, or you can do this algebraically by switching the numbers. You can do whatever works better for you. They're equally as good. So if I'm looking at the graph and I want to reflect point S over the y-axis, I'm counting the distance to the y-axis. 1, 2, 3, 4, 5. And then I'm going to keep going in the other direction. 5. 1, 2, 3, 4, 5. And here's my new S prime. The other way you can do it is when I'm reflecting across the y-axis, I just take the opposite of the x coordinate. So instead of -5, 6, I have +5, 6. Okay. The point T is 1, -2. If I do this visually, right, I'm 1 unit away from the y-axis, so I could use 1 unit to come back inside. Or instead of 1, -2, I switch this to -1, -2. So if it's positive, it becomes negative. If it's negative, it becomes positive. I take the opposite of x. And then U. I tend to count. I do it visually when it's easy. But that's not for everybody. Some people are like, no, give me the algorithm. So either way. And now I'm going to have a rotation. A rotation of 180 degrees actually just makes x negative and y negative. So for 180-degree rotation, whatever's in quadrant 1 gets moved to quadrant 3. And whatever's in quadrant 2 gets moved to quadrant 4. This one I don't do visually. I use the coordinates. Because you need to go in the opposite direction, right? So if S prime is over 5 up 6, then I want to go left 5 down 6. So S double prime is going to be negative 5 comma negative 6. Same thing here. So my coordinate is negative 1, negative 2. So I'm going to take the opposite. So it's going to be positive 1, positive 2. All right, and then for U, instead of 3, negative 4, I'm going to have negative 3 and positive 4. Here's my final answer. It's a good idea, again, to like make that stand out somehow. So whether you want to shade it in or you want to do it with a highlighter, or if you're using different colors, you know, kind of whatever works well for you. It will give you a heads up that sometimes, you know, when we're doing these practice questions, the problem might read very similarly. Given triangle STU with these vertices, what are the coordinates of, and maybe it only asks you for one of the coordinates. What's the coordinate of S after this transformation? And then you would just find one of the coordinates. But it's the same work, you just only have to move 1 point instead of 3. All right, example 5. A chance for you to try. All right, so this one is going to be your turn to give this a try. So I'm going to try to put up the information in pieces. So please pause this and see how far you can get in problem 5. Maybe all you can do is get those 3 points plotted, and that's fine. Maybe you can get the first step done with the dilation. Okay, maybe you can get all the steps done with the reflection also. So go ahead and pause and give that a try. Okay, so here is just the graph with the points X, Y, and Z plotted. So at the very least, I would imagine you've got this after you paused that video. So the first transformation I'm going to do is a dilation of 3. I'm going to go ahead and copy down all my points here. So X is negative 2, 3. Y is 1, negative 2. And Z is negative 3, negative 2. When I do a dilation of 3, I'm basically going to multiply all the X values by 3 and all the Y values by 3 for each coordinate. So instead of negative 2, I multiply by 3, and I get negative 6. And then 3 times 3 is going to give me 9. So I have a new point, negative 6, 9. 6, 7, 8, 9. Oh, barely fits. Awesome. And then same thing here for Y prime. 1 times 3 is 3. Negative 2 times 3 is negative 6. 3 down 6. And Z prime, negative 3 times 3 gives me negative 9. Negative 2 times 3 gives me negative 6. Negative 6. Okay. So I have a dilated triangle. That's the first step. Then I have to do the reflection across the x-axis. When I reflect across the x-axis, x stays the same, y changes signs. So maybe you were only able to do the first transformation, and this is as far as you got. Cool. Maybe you were able to get all the way there, which is awesome too. So reflection across the x-axis Remember, you can do this visually or you could do it algebraically, right? X is 9 units away from the x-axis, so I have to go 9 units in the opposite direction. All right? Or I do -6 and then I change the sign, -6, -9, and that gives me x double prime. So y double prime, I have 3, and then I change the sign of y, 3, 6, and then z, -9, +6. Oh, missed my mark for sure. Okay, there's my final answer. Maybe I want to highlight it so it stands out. Okay. All right, and I've got my answers for my coordinates below. Very cool. All right, so that wraps up 9.2. It's not a lot of new concepts. It's just kind of blending and bringing a lot of things together. It does introduce the whole idea of a composition of functions, a composition of transformations. But really the work is just performing transformations in the right order. Okay. All right, guys. Thank you very much. Take care. Bye-bye.